First law, inertia. Definition: an object at rest stay at rest, and an object in motion stay in motion with the same speed and in the same direction unless edged upon by an unbalanced external force. This image shows a bicycle standing still on the sidewalk. According to Newton's first law, the bicycles will remain at rest unless a force like someone pushing or riding it is applied. The inertia of the bike resists any change to its state of rest. If no unbalanced external force acts on it, it will not start moving on its own. Next one, in this photo, a skateboarder is gliding along a smooth, flat surface. Newton's first law explained that the skateboarder would continue moving in the same direction and speed if no external force, like friction or air resistance, were acting. However, in real life, the skateboard eventually slowed down due to this force. Without them, the motion would continue indefinitely, showing how inertia keeps moving objects in motion unless stopped by an unbalanced force.
Next is Newton's second law. The definition is the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Based on the picture, the woman is pushing a shopping cart filled with groceries, demonstrating how an applied force causes an object with mass to accelerate. The more mass the cart contains, such as heavy items like bottles, cans, and products, the more force she must exert to move or speed it up. If she pushes the cart harder, it will accelerate faster, showing the direct relationship between force and accelerate. Conversely, if the cart were empty, she would need to apply less force to achieve the same acceleration, clearly showing how mass affects the amount of force needed for movement. Second example, when the player swings his leg and kicks the ball, he applies a force to the ball. If the ball has mass, and because of the force from the kick, it accelerates across the field. If the player kicks the ball with more force, the ball will accelerate faster and travel farther. On the other hand, if the ball were heavier or the kick weaker, the accelerate would be less. This demonstrates how both the force applied and the mass of the object affect the acceleration, just as Newton's described.
Last but not least, let's look at the Newton's third law. It states that for every action, there is an equal and opposite reaction. This means that when one object exerts a force on the second object will exert a force of equal magnitude and in the opposite direction back on the first object. For better understandings, let's look at some of the Newton's third law examples applied in everyday life. First is when we walk, our foot pushes backwards against the ground. This action creates a reaction force from the ground that pushes us forward. Without this reaction, we will not be able to move effectively. This interaction is crucial for maintaining balance and momentum as we walk. Another example is while swimming. We push the water backward with our hands and feet. These actions generates an equal and opposite reaction from the water, propelling us forward. The harder we push against the water, the faster we move ahead. This principle is essential for effective swimming and is also observed in how fish swim.